Hey, you guys, it's Jerry Pinter. Welcome to part 4 of our lecture on chapter 5, which covers the discrete-time Fourier transform. In this part of the lecture, we'll look at the discrete-time Fourier transform and how to use it to solve linear difference equations. And this is analogous to what we did in chapter 4, I believe it was part 4 also, where we used the Fourier transform to solve linear differential equations in continuous time. And so in discrete time, instead of linear differential equations, we are dealing with linear difference equations, but we can use similar methods in the frequency domain using the Fourier transform to solve systems that are described by these equations. So let's get started. So as we did the same thing in chapter 4, I'm going to show you here sort of the derivation first, but we're not going to have to do this every time we want to use this method, but I want to show you sort of where the method comes from. So the idea here is that in discrete time, LTI systems are often described by linear difference equations. And again, this is completely analogous to the way that continuous time systems are described by linear differential equations as discussed in the previous chapter, in chapter 4. So here is our here's an example, sort of a general form of a linear difference equation. We've got all the y terms over here on the left, and on the right side are the x terms. Now remember, the y's those are the outputs of the system, and the x terms are the inputs of the system. So a linear difference equation, we can put y of n by itself here, and it has some coefficient here, a naught, which might be equal to 1. And then here is the first delay of y, so this is y of n minus 1, and its coefficient we'll call a1. And then we just keep going here, y of n minus 2, that's a second delay of y, and it has a coefficient a2, and so on and so forth. On the right side, we kind of do the similar thing. We've got x by itself here with coefficient b naught, and then x of n minus 1 has a coefficient b1, and so on as needed. So we can use the discrete-time Fourier transform, which we've learned about in this chapter, to find the following. We can find the system frequency response, h of j omega. From that, we can find the system's impulse response, h of n. And from the impulse response, we can immediately determine if the system is stable or not, just by inspecting that impulse response. And then, most important, we will eventually be able to find the system output, y of n, for any given system input, x of n. So in order to do this, we're going to follow a method just like we did in chapter 4. We're going to start with this linear difference equation here, and we're going to take the Fourier transform term by term. In other words, we're just going to take the Fourier transform of everything over on the left and take the Fourier transform of everything over on the right. And so that's what's shown here. The F here stands for Fourier transform. So, this first term, we've got a naught, and then we're going to take the Fourier transform of y of n, and then likewise, we're going to do that for every term in the linear difference equation. So the way we're going to proceed then is, and here again, I've written the linear difference equation in its entirety. That's what we're going to start with. And now you can see we're going to take the Fourier transform term by term. And what we're going to do here, just like we did in chapter 4, we're going to use the time shifting property. So for discrete time systems, if we have x of n minus n naught, where n naught is some integer, it's the amount of delay, then all we do over on the other side is we have the transform of x, which is x of j omega, and this is the delay term, right? We did this in several examples in earlier parts of this chapter. We have a delay term, which is e to the minus j omega n naught. And the value of n naught here, which is an integer, it's 1, 2, 3, 4, 5, etc., is just this whatever number is over here. So we're going to use the time shifting property, and we can do these Fourier transforms very quickly. So for example, the first term, we have a naught times y of j omega. All right, there's no time shift there because it's y of n. The second term, we have a1, and then we have y of n minus 1. So we've got a time shift or delay where n naught here is equal to 1. So we're going to pick up a factor of e to the minus j omega times 1. So that's this term right here. You can see we've got e to the minus j omega times y of j omega. For the next term, we've got a2, and now our time shift is 2. So we've got e to the minus j2 omega times y of j omega. And if this keeps going to higher order delays, we would just keep using this property accordingly. Now let's go to the right side. Here we're talking about the x terms. So the first one is just b naught times x of j omega. The second one is b1, and here it's delayed by 1, so we've got e to the minus j omega times x of j omega, and then we would just continue as necessary for any other terms that might exist up here. So what we can do next is notice that all these terms on the left side have a y of j omega. There's one here, there's one here, and there's one here. So we could factor that out, and that's what I've done here. And what's left in the parentheses here are the coefficients, the a naught, a1, a2, etc., and the delay terms. So a1 has a delay of e to the minus j omega, a2 has the delay e to the minus 2 j omega. So we're just doing some basic algebra here, nothing that difficult. And then likewise on the right side, we can factor out the x of j omega because every term will contain that. So here's the x of j omega factored out, and what's left inside the parentheses are all the b coefficients and the delay terms that are associated with them. So at this point, remember the convolution property. In the time domain, if we've got x of n going into a system that has an impulse response h of n, then the output y of n is equal to the convolution of x and h. But we're working now in the frequency domain. So remember the convolution property says that in the frequency domain, the input here is x of j omega. The output, y of j omega, is equal to just the product. There's no convolution. It's the product of x of j omega and h of j omega. So we can solve this little equation right here, y equals x times h. So obviously h is equal to y divided by x. So here is our frequency response. The frequency response of the system is the Fourier transform of y divided by the Fourier transform of x. And by using this expression up here, right, if we divide both sides by x, so we get y over x over here, and then we divide both sides by all the a coefficients, we end up with this relationship right here. And this is, again, very similar, almost, exactly the same as what we did in chapter 4, but now the delay terms look a little bit different. So what we've got here on top in the numerator, these are all the x coefficients that were all over here, the b coefficients. So we've got b naught plus b1 e to the minus j omega plus b2 e to the minus j2 omega, etc., etc. And then in the denominator, we have all the a coefficients, which remember the a's are corresponding to the y Fourier transform here. So we've got a naught plus a1 e to the minus j omega plus a2 e to the minus j2 omega, etc. So the idea here is that everything I've just shown you, we're not going to have to repeat all that. We can just use this result right here, and we can write the frequency response, h of j omega, from a difference equation by simple inspection of the linear difference equation coefficients. In other words, we're going to just write this frequency response just by looking at the difference equation up here. We don't have to do all these steps, all right, because we've already proved that they're valid. So let's go ahead and do an example where we're going to use this Fourier transform method for solving a linear difference equation. So let's suppose that we're told that an LTI system is described by the following linear difference equation. We have y of n minus 3/4 y of n minus 1 plus 1/8 y of n minus 2 is equal to 2 times x of n. So before we go ahead and use our new method here, let's just go ahead and construct a block diagram of this system. So this is a good review from chapter 2. Remember, the way to draw a block diagram of this system is we take this y of n and put it by itself on the left side right here, and move all these other terms over to the right side. So this is the difference equation just rewritten. The reason we do this is we can now draw the block diagram directly from this difference equation here. The reason is that y of n, which remember that's the output over here on the right, here's the input x of n over here. The output is the sum, it's equal to this term plus this term plus this term. So we know we're going to have to add three things together to get the output. So here's our summer, our adder, okay, this symbol here. And let's start with the easy one here. We notice that the output is equal to 2 times the input. So here's the input, x of n. We multiply it by 2, and we send it into the adder. The next term, let's do this one here. It's 3/4 times y of n minus 1. So here's y of n. We're going to put it through a delay to get y of n minus 1, and we're going to multiply it by 3/4 and throw it into the adder. The last term right here, minus 1/8 times y of n minus 2, we need a second delay. Well, we've already got y of n delayed once right here, so let's take this signal, which is y of n minus 1, and put it through another delay element, which gives us y of n minus 2, and then we multiply it by minus 1/8, because that's the coefficient here, and put the result into the adder. So we've got these three arrows right here represent these three terms up here, and the output here of this adder is, of course, the output of our system, which is y of n. So that's how we can quickly draw a block diagram from a difference equation. And again, this is nothing new. We did this back in chapter 2. Okay, so now let's find the frequency response by inspection. So all we need to do is let's start again with our original linear difference equation that was given to us. And from here, I'm just going to write the frequency response directly. So remember, what goes on the top are the coefficients of the x's over here. So all we have is x of n, so that's just a 2. That 2 comes right up here. All right, now on the bottom, you can see there's a y of n. That's going to give me this 1. We have minus 3/4 or 3/4 of y of n minus 1. So here's the minus 3/4, and remember, a delay of 1 means a factor of e to the minus j omega. The second term here, we have 1/8, you can see it right here, and we've got a delay of 2, which gives us a factor of e to the minus j2 omega. So here we have written the frequency response of this system just by simple inspection. And we can write it without really having to do any work at all. We just have to remember which goes on top, which goes underneath, and how to handle these delays using these delay terms down here. Now, in order to make some sense of this, what we're going to do next is factor the denominator here. Now, if you look at this, it's not very obvious at first glance how to factor this. But one thing you can do here is you can, a little hint here, especially the first few times you do this, is let e to the minus j omega equal some number, call it a. So this denominator here becomes 1 minus 3/4 a plus 1/8 a squared, right? Because it's got a 2 up there. So we can rewrite this like this, 1 minus 3/4 a plus 1/8 a squared. And this is much easier to factor. You can see just by trial and error, this is equal to 1 minus 1/4 a times 1 minus 1/2 a. And now we can plug in, remember, a is e to the minus j omega, and so that's what I've done in this step here. So it's a fairly straightforward way to factor expressions like this. And so here is our frequency response then. Here is our result. Now, in order to we're going to want to, find the inverse Fourier transform of this thing. And we can't do it directly because this is not one of those known forms. So what we have to do here is expand this expression using partial fraction expansion. And so again, this is something we've already done in this chapter, so I'm not going to go through the details. This is just, simple algebra to find out what we're going to break this frequency response into 2 terms. One will give a coefficient of a, and the other has a coefficient of b. And remember, in order to find a and b, we just use all the regular tricks. To find a, we multiply everything by 1 minus 1/4 e to the minus j omega, and we get this expression here. And then in order to get a by itself, we can let 1/4 e to the minus j omega equal 1, or in other words, e to the minus j omega equals 4. And so when you plug this in, we end up with a equals -2. So again, I'm kind of glossing over this quickly because you've already learned how to do partial fraction expansion. And if you're a little rusty on this, you should review the previous videos from this chapter or go through the steps at your own pace, so that you can make sure you know how to do this. And then using similar method, you find that b is equal to 4. So here is our frequency response in its expanded form. And again, the reason we're doing this is now we can invert these two terms by inspection, because remember that for an exponential type sequence, a to the n times the step function u of n, that leads to a Fourier transform of 1 over 1 minus a e to the minus j omega. So just by comparing these two terms, this one here, obviously it's got a 4 out in front, so that's the 4 there. And by comparing this with this, we can see that a is equal to 1/2. So we're going to have 1/2 right here. So it's 1/2 to the n times the step function u of n. And then the second term, we have minus sign 2. So there's the -2. And by inspection, we see that a is equal to 1/4 in this second term. So we have 1/4 to the n times u of n. So this is our impulse response, okay? And the other thing, we can see that we can plot this if we want. So here's the impulse response plotted. And you can see that this impulse response, it decays to 0 for large values of n. And again, you can see that here, since these numbers inside the parentheses here, there's a 1/2 there and a 1/4 there. Since those numbers are less than 1, when n gets really large, both these terms here are going to go to 0. So this represents a stable system. The impulse response is decaying to 0, and remember, that's our definition of how we can tell if a system is stable or not. Okay, so the next thing, let's suppose that we're given an input to the system as follows. We're told that the input, x of n, is equal to 1/4 to the n times a step function, u of n. So this is what the input looks like. So our goal now is to find the system output. This is the same system. What is the output sequence y of n for this input sequence? So instead of, remember in chapter 2, we would have used convolution to find the answer, but now we're going to find the output using our frequency domain methods here without using convolution. So to do this, let's find the Fourier transform of this x of n right here. And again, we're just going to use this same Fourier transform pair that we've been using over and over in this chapter, and we can immediately write that the Fourier transform x of j omega is equal to 1 over 1 minus 1/4 e to the minus j omega, because a is obviously equal to 1/4, as shown right up here. The output, remember, this is the convolution property, is equal to x times h, right? We don't have to do a convolution here because we're working in the frequency domain. So we have this is our x, and we multiply that by the frequency response h of j omega from the previous couple of slides, and we end up with this Fourier transform of the output right here. Notice this first term here is squared because there were two of them. One of them was in x and the other one was in h. And at this point, the last step is all we have to do is find y of n. We have to take the inverse Fourier transform. Obviously, we can't do it just by looking at this thing because we've never seen anything with this form before. So again, partial fraction expansion comes to the rescue here, and we have to expand this thing out. Now, I didn't do the details here of the partial fraction expansion just to save some time and space here. One thing I will note, though, this form here is a little bit different because it's got this first term down here is squared. And so if you look up the rules of partial fraction expansion in any math text or just Google it online, you'll see that when you have a term that's squared, you have to include that square term in the partial fraction expansion. So we have each of these terms by themselves, that's here and here, and then we have the term squared. So there's actually three partial fraction coefficients, A, B, and C, but they can be found using the same methods that you've learned earlier in this chapter. And so when you do that, you come up with 8, 4, well, it looks like 8, -4, and -2 for those partial fraction coefficients. So here is the Fourier transform of the output of this system. So then our last step is to invert y of j omega. And again, that last term, which had the square, is something new that we haven't done here. So I sort of cheated here, and instead of trying to derive the whole thing, there's a nice table in your textbook that shows Fourier transform pairs, and that last term, which has the square, is found in table 5.2 in your textbook, and it leads to this term right here. The first two terms in y of j omega are easy to invert because those are just like the ones we've done in the past. But that last term on the last slide that had the square in it leads to this form here. There's a n+1 term in front of the 1/4 to the n. So here is the final output of the system. So basically what we've done here is, starting with that difference equation, we've built the system. We've got a block diagram of the system here, and this is the input sequence of the system, which was given to us, and using Fourier transform methods, we have derived the output of the system. Looks something like this, which is described by this expression right here. We can change gears a little bit here and work backwards, and instead of finding the impulse response from a linear difference equation or a system block diagram, we can work backwards and actually design a system from a given impulse response. So the idea here is one kind of way to think about this is, suppose that we know a system's impulse response. So and let's imagine we have some unknown system inside this box here. So this is, in engineering, this is called a black box because we don't really know what's inside here. Well, one way we can sort of probe to figure out what's inside here is send an impulse, a delta function, into this system. We know this is a discrete time system. We just don't know any of the details. So if we put an impulse in, obviously this black box system here is going to spit out an impulse response, h of n. So by analyzing h of n, we can actually work backwards and figure out what is inside this box. So the goal is to design a system that has a given impulse response, h of n. So the method is the following. We're going to start with some impulse response, h of n, that's given to us. We're going to determine h of j omega, which is the frequency response, just by inspection of h of n, okay, just by doing a Fourier transform. And then from h of j omega, from the frequency response, we can determine the system's difference equation. And then finally, we can design the system using adders, multipliers, and delays from the difference equation. So let's go through these steps. Here's an example of this method. Suppose we're given the following impulse response. H of n is equal to 3 times 1/2 to the n minus 2 times 3/4 to the n, and all of this is multiplied by a step function. Our goal is to design a system with this given impulse response. So the first thing we can do here is, from this impulse response, we can write the frequency response. And again, remember these two terms here in the impulse response, this is nothing new. This is the exponential decaying exponential function that we've been using all along. And so the transform is 1 over 1 minus a times e to the negative j omega. So by using this result right here and applying it to these two terms right here, we get this expression here. Now, with this expression, what I'm going to do here is combine, kind of the opposite of partial fraction expansion. We're going to take these partial fractions and we're going to combine them back together. So remember how to do this, how to add or subtract fractions. We have to have the least common denominator. So I'm going to have to multiply this first term by this denominator on top and on bottom. And for the second term, I'm going to have to multiply top and bottom here by the denominator over here. So this is no different than, when you're adding or subtracting fractions. Like if you were going to try to add 1/2 plus 2/7, right? You would have to do the same kind of thing. You would have to use those least common denominator methods. Okay, so once we've done that, I've got this form here, and now I can distribute the 3 inside here and the -2 inside here, and write out the top. It's going to look like this. I won't go ahead and read off all these terms. And then finally, we can simplify. Notice there's an e to the minus j omega here and e to the minus j omega here. So we can combine them together. And the other thing I did down here on the bottom is I FOILed out these bottom terms, first, outside, inside, and last, and came up with this expression here. So here is, and then the last step, I'm going to get rid of these fractions. So 5/4 is 1.25. Here's 5/4 again, 1.25, and then 3/8 is 0.375. So this is our frequency response, and the reason we wrote it like this is from here we can write a difference equation for this system just by inspection. So remember that what goes on top here determines the x side over here of the difference equation. So this 1 here gives us x of n. We have minus 1.25, that's right here, minus 1.25, and remember e to the minus j omega, that is a delay of 1. So we have x of n minus 1. On the bottom down here in the denominator, this determines all of the y coefficients. So the 1 here gives me y of n, the minus 1.25 is shown right here, and we have e to the minus j omega, which means y of n minus 1, it's a delay of 1. Then we have plus 0.375 right here, and this is a delay of 2 because it's e to the minus j 2 omega. So we have y of n minus 2. So basically, from this frequency response, we can write a difference equation for this system just by inspection, and here it is. The next step is, remember our goal here is to design a system, like a block diagram of this system. And so to do this, remember, once you have a linear difference equation, just solve for y of n. Put y of n all by itself over on the left, put all the other terms over here on the right. So notice that y of n is the sum of 4 terms, this term, this term, this term, and this term. So I'm going to put an adder here, okay, and this is x of n coming in on the left, this is y of n coming out. We know that the output here has 4 different terms that make it. All right, so let's do the easy ones first. Well, notice there's an x of n right here, okay? So that means x of n goes into the adder. So that takes care of that term. Here is another x term. It's x of n minus 1. So I'm going to take x of n and put it through a delay to get x of n minus 1, and then notice I have to multiply it by negative 1.25. So that's what this coefficient right here means. In a block diagram like this, whenever you see just numbers near the arrows, those numbers just mean that's what we're multiplying this signal by. All right, so this arrow here represents this term here. Then we've got these 2 terms. All right, well, they're both y terms, and they're both delayed. All right, so this first one is delayed by 1, so I'm going to take y of n, bring it through a delay to give me y of n minus 1, multiply it by 1.25, and throw it into this adder. That's that term there. The last term we need to take care of is this one. I've got a second delay. It's y of n minus 2. So I'm going to use this term here, which is already y of n minus 1, and send it through another delay element to get y of n minus 2, and finally multiply it by negative 0.375 and throw it into this same adder. So we've got all these 4 arrows here that are going into the adder right here represent each of these 4 terms. So this is how you can quickly draw a block diagram from any difference equation. Okay, it's actually fairly straightforward once you know basically the method of how to do it. So here is our block diagram for that system that was described by that given impulse response. So basically, we've figured out what's inside the black box here. So here's one that's actually a little bit more straightforward, but I'd like you guys to try this one at home by yourself. This is something normally if we were in the classroom, you'd be working in a small group to do this on your own. So this activity, it's a system design activity. So you're given an impulse response, h of n, which is equal to 3 times 2/5 to the n times a step function of u of n. And your goal is to design a system that has this impulse response. So here are basically the steps again, which will help guide you. You're going to start with this impulse response, and you're going to first find the frequency response by inspection, okay, using this same result like we've been using all along. From the frequency response, step 3, you're going to write the difference equation, all right, by inspection. And then rewrite the difference equation with y of n on the left side, and finally draw a block diagram of the system, design the system using adders, multipliers, and delays using that difference equation. So go ahead and pause the video here and get out some scratch paper, and you can look back on how I just did that last example, but see if you can come up with the system design for this given impulse response. Okay, here are the solutions to this activity. So you were given the following impulse response, 3 times 2/5 to the n times u of n. The frequency response just comes from inspection. We have a 3 out in front, that goes on top. We have 2/5, that's the value of a, so it's 1 minus a to the e times e to the minus j omega, so a is 2/5. And the difference equation, we write that directly from the frequency response. So the 3, that goes over here on the right side and determines the x's. So it's 3 times x of n. On the bottom here, this 1 gives me y of n. And we have minus 2/5 or minus 0.4. And then remember, this is a delay of 1. E to the minus j omega gives me y of n minus 1. So here's the difference equation. The next step, move this term over on the right side. In other words, solve for y of n. So y of n is equal to 3x of n plus 0.4 times y of n minus 1. And now we can draw the block diagram for the system. Notice the output y is the sum of two terms. So the first term, the easy one, is 3x. So here's x coming in, multiply it by 3, and put it into this adder. The second term is 0.4 times y of n minus 1. So I'm going to take y of n, I'm going to bring it through a delay to get y of n minus 1, multiply it by 0.4, and put it into the adder. So these two terms here, these two arrows here, represent each of these terms here, and the output of the adder, of course, is the output of the system. So there is our final answer here. So, from this given impulse response, we can design a simple discrete time system that has that same property and impulse response. The last example I'm going to show you kind of real quick here. It's actually a bit more advanced and a little more challenging than what we've done up to date, and you won't have to do anything like this on the homework or the worksheets. But I did want to show you this because it's sort of a practical design. This is called a digital oscillator. In other words, it's a digital or discrete time system that produces a nice sine or cosine output, which can have important applications in communication theory and digital radio and things like that. So this is the difference equation that we're going to start with. So it's pretty much just a normal difference equation. The one thing that's different about it is that this coefficient here in front of the y of n minus 1 term is 2 times cosine of omega naught. And it turns out that omega naught will end up being the oscillation frequency of the oscillator. And that's certainly not apparent at this point yet, but you'll see later on when it comes out like that. The other thing I'll mention here is the input of this oscillator is just a delta function. So a delta function sort of gets this thing started, and the impulse response of this system here will be an oscillating output. In other words, it's not a stable output because it doesn't decay to zero. It just keeps oscillating up and down, just like a cosine function or sine function. So from this difference equation here, by solving for y of n, we can draw the following block diagram for the system. And so, here's y of n, goes through a delay, and it's multiplied by 2 cosine omega naught. That's that term right there. We send y of n through another delay, we get the y of n minus 2 term, multiplied by minus 1, because this term has been moved to the other side, and it's added to the x of n here. So this is the block diagram for the system. You can see it's a pretty simple system. It's got 2 delays, and it's got 2 adders here, and then it's got a multiplier here. Remember, this term here means we multiply the signal by 2 times cosine of omega naught, and we can pick and choose whatever omega naught we want, depending on how fast we want this thing to oscillate. So the goal here in the next several slides, and again, I probably won't go over it in a lot great detail, is to find the output of this system here using discrete-time Fourier transform method. So let me just show you sort of what I've done here. And as I should mention, there are several steps, and some of them, there's quite a bit of some tedious algebra involved, so I'm not going to go through the details here. If you're curious about this, you're welcome to go through it on your own, at a more step-by-step pace. But basically, what we're going to do here, we start again with the linear difference equation. The next thing we can write the frequency response by inspection. So this is exactly what we've been doing in this part of the lecture. On the right side, x of n, that gives us a 1 on top. And remember, on the bottom, these are all the y terms. So I've got y of n over here, that gives me a 1, minus 2 cosine omega naught. Remember, this is the coefficient here. So I have minus 2 cosine omega naught, and y of n minus 1, that's a delay of 1, which means we have e to the minus j omega. And then this term here, y of n minus 2, that's a delay of 2, so it's e to the minus j 2 omega. Okay, so this is just nothing, different than what we've been doing in this chapter. Now, here's where it gets a little crazy. In order to handle this frequency response here, I'm going to factor it. And to do this, you can see I'm defining a variable called z, which is equal to e to the minus j omega. So that the denominator here looks like this in terms of z. And I'm going to factor it using the quadratic formula, which of course you're familiar with. So it's it's opposite of b over 2a plus or minus 1 over 2a times b squared minus 4ac. And when you do all this, when you plug all this into the quadratic formula, you end up with this form here. Now, since this term inside the square root, the radical term here, is actually negative, this is going to be an imaginary term. So what I've done here is factored out a j, which remember is the square root of -1, and then I can flip the order of what's inside the square root. And so instead of cosine squared minus 1, it's 1 minus cosine squared, but remember, that's sine squared. So when we take the square root of sine squared, I get a sine. So this thing simplifies down to this form here, and then by using Euler's formula, I get the 2 roots of my factored denominator here are these simple terms here, e to the plus or minus j omega naught. So when I substitute those back into here, here is my factored form of the frequency response now. Okay, from there, we can use partial fraction expansion. So in other words, take this thing here, break it up into 2 pieces, call them A and B, use all the regular methods to figure out what A and B are, and now we get this form down here for our frequency response. Now it looks like obviously things are getting worse before they get better, which is often the case in these challenging problems. The next thing we can do though is take the inverse discrete-time Fourier transform by using this same old Fourier transform pair that we've been using over and over again. And so after doing that and doing a little bit of rewriting by multiplying the top and the bottom by some terms here, we can put the frequency response in this form, which then means the impulse response, h of n, ends up looking like this form down here. Now again, this looks like a mess, but one thing you'll notice between this first term here and the second term here is they are the same except for the sign of j. Here I have a positive j, over here is a negative j. Up here I have a minus j, and over here I have a plus j. So that means and then by the same thing here, a negative j here, positive j over here. So these two terms are complex conjugates of each other, which is a good sign because we can now combine these and simplify them. So there's a very convenient property of complex numbers. Whenever you have a complex number z and you add its complex conjugate z star, the answer is 2 times the real part of z. So if we call this first term z and the second term z star, then all we have to do is find the real part of z, of this here, and multiply it by 2. So that's what I did in these next several steps here. And you can see, there's a fair amount of algebra here using complex numbers. Finally, I get it down to this form here. In step 8, I FOILed it out and just kept the real parts because that's what this real symbol out here means. We're throwing out the imaginary part, just keeping the real part due to this property shown up here. And so here finally is our impulse response, which is the output of the oscillator. Notice there's a cosine of omega naught n plus cotangent omega naught. This is just a number depending on what omega naught is. And then we have an oscillating sine term here, sine of omega naught n. So kind of to summarize everything we did here, we started with this difference equation and we drew this system block diagram for our digital oscillator. The input of the oscillator is just a single impulse that gets the oscillator going. It's like you need to just give it a little kick to get it to start to oscillate, and then it just oscillates from there on. The impulse response, which is the output, y of n is basically h of n here, is this function here, and you can see it's a cosine and a sine term added together. And so I plotted this in Excel using a couple different frequencies. So first I chose my oscillation frequency omega, which is this omega naught here, here, and here. I plugged in pi over 8, which is about 0.39, and look at the output of the system. You can see it produces a nice sinusoidal output. It's oscillating. And then I also did it here with a much lower frequency. I set omega equal to 0.1, and you can see again a beautiful, nice cosine or sine function here, a sinusoidal output with a much lower frequency than over here. So this is a very practical digital system here. We've got it's an oscillator, and the frequency of oscillation, whether you want it to oscillate fast or slow, is set just by this coefficient here, by what value we multiply this signal at. So basically, this is a variable frequency digital oscillator. And that is the end of our lectures here from Chapter 5. Remember, there is another part to this lecture, which is optional material that you're welcome to look at in the notes, which will be posted on Cougar Courses. And those notes will explain some of the extra credit opportunities if you're interested in looking at the discrete Fourier transform, the fast Fourier transform, or image processing. So until then, I will see you when we move on to Chapter 6 next. Take care and goodbye.